The reason I say that is I asked for two different things. I believe I asked for the tension and the acceleration at some point in the problem, right? So it says the force of friction acts on the table at first, and then part C, the table's waxed, and you have to redo the whole thing without friction in place. So this problem has, basically both versions of this problem, one with friction and one without. And so just trying to get this drawn so everybody has a chance to see it. There we go. So it is not uncommon for the mass to be given as multiples. So the box on the table has 3 times the mass as the box off the table. That's what this is stating. And in the beginning of the problem, friction is holding the system in place. Now, that's the least interesting of the two examples, but if those are the ones we have to do, I would always recommend that you start every problem in the same place, which is a free body diagram. And I know you're tired of hearing me say that, but I told you you'd be tired of it by now, and you probably are. So I will start with the free body diagram. 3 mg downwards. I could write weight, but I'm writing 3 mg because there's 2 different objects, each with weight. I want to differentiate between them. There's also an upward force, normal, and I'm drawing those arrows to be the same size. And I will have a tension force to the right and friction to the left. Net force equals 0. We are told the box is at rest on the table. It is held in place by friction. Now, I can continue. Because net force equals 0, I can say net force in the x direction equals 0 and net force in the y direction equals 0. This is not particularly interesting, but if I'm going to make a coordinate system, x and y look good for you guys. Doesn't matter positive and negative, net force equals 0, so it's staying in place. X direction will be tension minus friction equals 0. Y direction will be normal minus weight equals 0. So I know from the beginning of this problem that the tension equals the friction and the normal equals the weight. Now that's not what the problem asked. The problem asked, find an expression for the force of friction in terms of m and g. This is the force of friction in terms of t. So I can't stop here. I need to continue. So we can't be done now, but we have more information to use, right? The 2 masses are connected, so the next thing I'm going to do is I'm going to look at the other mass. I'll draw a free body diagram for it. mg downwards, tension upwards. The net force on this mass also equals 0. I'm not going to bother with a coordinate system. It's very one-dimensional. So T minus mg equals 0. T equals mg. So now it's at this moment that I realize I have 2 ways of showing what the tension is. I could eliminate tension between these 2 and get a new expression for friction that doesn't have tension in it. Does everybody understand what I just said? To make sure that we're all on the same page. All right, so basically I'm going to say friction equals mg and be done. Because friction equals tension and tension equals mg. So let me answer your question with the full answer so that you know why I'm saying no. But let me make sure your question is right. If you have 2 objects connected over a pulley, are the tensions always going to be the same? Now the answer is no. They're not always going to be the same. And the reason is because if your pulley also has inertia, then it will take an unbalance of those tensions to get the pulley to turn. So our pulleys are for right now are massless and have no inertia. So for the time being, the answer is going to be okay, yes, as long as you see something that indicates that the pulley has no friction or is massless or both. Does that make sense? Now, that's not true in the future. In the future, it will take force to get the pulleys to turn, and that force will come from the tension, and therefore some of the tension in the rope will be changed in order to get the pulley to turn. But that's second semester. We got some time. Continue? All right. Here's where I would stop you first and remind you that it's at this moment you can test your answer to see if the algebra you've done is okay. Now, this one was not particularly hard, mind you, and I'm going unreasonably slow, I think. But I'm just trying to be patient and particular. This product would have units of kilograms for mass and meters per second squared for G. And as I know, that's the unit for newtons. If you test the units that you get for an expression, it's an easy way to see if your algebra was done correctly. If the units don't work out, if you get units for a different value, then you likely made an algebra mistake. And that's a good way of testing whether you got the algebra done right. Look, I've watched a lot of you do this work, and you're applying all the steps correctly, and you are getting the result of what applying those steps will do. But you're getting stuck there, or the math is getting in the way of you going any further. Well, we got to find a way beyond that. This is a way to help you check. Now, this is not the more interesting of the two examples. The more interesting example went on further to ask what would happen if there was no friction, and you were asked to find the acceleration of the system in terms of m and g. To me, that's a more interesting question. So you should probably understand that I'm going to definitely want to ask that on the test tomorrow, right? So if you get stuck with one like this, and you might, you know I'm going to ask about the acceleration of that system. Now, the moment there's no friction, this problem does change. Not dramatically so, but this friction goes away. So I'm just going to erase it right here. So now there is no more friction acting on that mass. What's that going to do? Well, it's going to mean that this is no longer 0. This is going to be 3ma. Let me make that very clear because that's kind of small on the board, and I want to really highlight that a little bit better. 3m times a. Net force equals ma, but that m refers to the mass of the object. Our object has a mass of 3m. So you need to make sure that you put in the mass of the thing that's moving. For expression problems, that can be difficult, especially if your thing is 3m. You will, or you might forget. Now, a few of these things are going to change because of that. So I'm just going to kind of erase everything. Because I know the system is accelerating, it's always best to have a unified direction for positive. I'll put that unified direction around the pulley because I feel like the pulley is a good place for it. By putting a plus there, it means that anything in this direction on the mass is going to be positive, and anything on this direction on this mass is going to be positive. Okay? And now I'm going to use that in dealing with my net force. For the 3m mass, I'm going to have tension equals 3m times a. In the y direction, I'm going to have the same thing. Normal minus 3mg equals 0. Over here, net force now equals ma. This one's just m, so I don't have to worry about 3m or 2m or anything like that. It's just m. I'm going to make downwards positive. So net force is going to be mg minus tension equals ma. Now, just so you know, the tension had to be reduced here. A lot of students will get this wrong, but I want you to understand the tension had to be reduced. It had to be less than what it was before. Before, the tension was mg. But the only way this box accelerates is if the tension is less than the weight of the box, right? This box right here, if the tension upwards is the same as the weight of the box, the net force is 0 and it does not accelerate. The only way it accelerates is if the upward tension is less. I'm saying this because I'm thinking about discussion questions and the way in which you would answer them. And an easy discussion question here is to ask, why is the tension less? So be mindful. That's a great discussion question. So getting back to the actual work of this problem, I have an expression here for the acceleration of the system, but it has t in it, so that can't be the answer. And I have an expression here for the acceleration of the system, but it also has t in it, so it can't be the answer. I need the acceleration in terms of the mass and g. So I have to eliminate t between these two. So when you ask yourself, to what degree do I have to do these expressions? Well, you at least have to get rid of any variable that's not listed as being allowed in your answer. So I'm going to eliminate t by substitution. That's what I'm going to do. I'm going to put 3ma in for t right here. Now, that's not the way I would do it most of the times. Most of the times I'll just add these two equations together. But I think most of you do substitution. So I'm going to stick with what you guys tend to do. So mg minus 3ma equals ma. Now, you guys love to do this, but you usually do it, many of you do it incorrectly. But I will point out there's an m in every term. Do you see that? Even before I do any math, I could cancel out the m's here. I'm not going to, only because you guys do that so frequently. I don't want you to get in the habit and make a mistake. I'm going to add 3ma to both sides and get mg equals 4ma. Am I okay? Anybody having any trouble with this? Okay. I'm solving for a. So a equals mg divided by 4m. Cancel out the m's. I expect you to do that. And my answer for a is g divided by 4. So there's a couple things that you should notice in this answer. First, g is in it, which means the units of my answer are meters per second squared. That's a unit of acceleration. Am I trying to find acceleration? Yes, so the units work out. It's likely I did my algebra correctly. Second, look, the system accelerates at less than g. That's important. A lot of you think it would accelerate at g if there was no friction, but that's not true. Even when we did the lab, it doesn't do that. It accelerates at less than g because a little mass is accelerating a whole bunch of stuff. And a whole bunch of stuff has inertia. And therefore, it's not going to accelerate as if the whole thing is being accelerated by gravity. Only a part of it is. Any questions yet? All right. The last part asks for the tension. Generally, to get the tension, once you have the acceleration, all you have to do is substitute again. This was two equations with two unknowns. The unknowns were t and a. So I'll get t through substitution. T equals 3m times a, which is g over 4. Now you could stop here, but no, I would like you to go a little further and collect the numbers. 3 force mg. You won't be marked off if you write yours as 3m times g over 4, but you do understand why I'd prefer to see it as 3 force mg, right? For one, it tells me that the tension is less. It was mg before, and now it's 3/4 of mg, so it's clearly less. But also, it collects m and g together. I can look at those units, see if they have the units of force. They do, kilograms, meters per second squared. Tension is a force, so the units work out. So, friction is less than equal to mu times the normal force. This is static friction, right? The coin is in contact with the record and doesn't slip with respect to the record. And they asked, what is the maximum amount of available friction? Well, it's an inequality. The maximum amount will be when it's an equality. That's the maximum. No, it's not the answer. To get the answer, I got to put everything in that I was given. And I'll need to figure out the normal force. So let's do the forcey stuff. Net force in the x direction equals ma. And net force in the y direction equals 0. I didn't draw a coordinate system. I really didn't think I had to. Is that all right? Now, the object's traveling in a circle, so that makes this A centripetal. Put the little C there just to remind me. But I don't need to know any of that to know that in the y direction, normal minus mg equals 0 and normal equals mg. I'm saying that because they want the frictional force, and all I need to figure out the frictional force is the normal force. So, mu s mg. They tell me that the coefficient of static friction is 0.4. The mass of the coin is 10 grams, and G is 10. So 0.4, mass of the coin is 0.01, and G is 10. Any questions about any of what I put on the board? All right, 10 times 0.01 is 0.1. 0.1 times 0.4 is 0.04 newtons. That is the maximum amount of static friction that there is. That's a whole lot of text message. That's a lot of hospital stuff. Okay. So, how about that net force in the, I didn't mean to do that. That net force in the x direction is equal to MAC. The reason I'm reminding you that is because the maximum friction is 0.04, right? So let's put these pieces together. The only thing that keeps it traveling in a circle is friction. And MAC is actually mv squared over r. Are we good so far? Just putting down what we already know. Now, going to a page where I have a piece of, I say fresh piece of paper, but that's a little ridiculous, isn't it? Fresh piece of iPad screen. I don't know. So here we go. Again, I love this question. So there's my dime. And we're asking, let's say it's right at the edge. So this edge is 31 centimeters away from the center. And it's going around, we're told, 33 1/3 rotations every minute. Everybody got it? All right. Look, you can do this. It's a conversion problem. Trying to figure out its speed. That is a speed in rotations per minute. Let me ask you, how far does it go every one rotation? Can you figure that out? What would we call that? A circumference, that's right. So we could replace circumference from rotation, right? So for every one rotation, we get 2 pi r circumferences. This will be in, hopefully, meters. Now the rotations cancel out and I get meters per minute. That's probably not what I want. I want meters per second. So I'll probably have to do another unit multiplier. I always do conversions with unit multipliers. I feel like it's not the best way, but it's the most visual way. I want to cancel the minutes. They're in the bottom. So I need to put minutes in the top here. And I want to be left with seconds. So I'm going to need one of those fancy conversions. Pretty sure there are 60 seconds in every 1 minute. How's that look? Is that okay? So I need 33.3 times 2 pi r, all divided by 60. I just dropped all the ones, and that will be my answer in meters per second. See, I think you could have done this. By the way, for those of you watching at home, 0.31 meters is the radius. I'm going to wait patiently while you guys bang away. And good luck. See, I can do the math, and I'm not so bad to look at. You know, I get it all. It's like the full package, except for my trashy shirt. All right, so I don't have to do the 45 one, do I? Good. D. What is the farthest away from the center the dime can be placed and stay on the record at each speed setting? That's a tough question. Not really. But I tell you it is to make you feel like it's harder than it is. Look, you just found both speeds, right? Or at least one of them. I will remind you the other stuff written down, the speeds, and rewriting that. F equals m v squared over r. F was 0.04. M was 0.01. V, we just did. So 0.04 equals 0.01 times 1.08 squared over r. I don't feel so bad asking this one. 0.04 divided by 0.01 is 4. Divided by, well, actually I don't have to do divided by, 4 equals 1.08 squared over r. So r equals 1.08 squared divided by 4. I can do my math better than you guys. You probably should cross multiply. Some of you screw this up badly all the time. And it makes me bat crap crazy. And I recorded that because it does. You guys who can't do that problem and solve for r are just like the bane of my existence sometimes. I don't mean that mean. I just mean I hate having to go back and reteach algebra. So for those of you who can't do it, 4 equals 1.08 squared over r. To find the answer, try multiplying both sides by r. That will make this side 4r and this side 1.08 squared. And I know I'm insulting some of your intelligences. I'm not talking to you. I'm talking to the people who, on their test, I see them do it wrong. And they know who they are. If I single them out right now, they'll say that I'm mean. So I'm not going to. Besides, this gives me an answer that makes sense. Doesn't it? Like 28, 29 centimeters? What is it? 29. That's kind of nice. That's still on the record. Listen closely, folks. If I was trying to screw you, I would do this problem in such a way that one of these answers was like 45 centimeters. Because then you'd have to say, you can't place it on the record because the record's only 31 centimeters to see if you're really paying attention. Right? If that number's bigger than the radius of the record, can you put it on the record? No. This is Inktober. I'm doing my best work here. I'm living my best life. Except this guy's supposed to be on the ground. There we go. You catching all this, Stephen? Yes. Is this just like physics back where you were? No. Sorry. It's usually more business than this, but I'm just not feeling myself today. But this will all be on YouTube later in case you're wondering. All right, so you want just the second part where the guy's accelerating upwards? What's the maximum acceleration he can do and the guy's still staying in contact, or what's his mass? I can't remember what his problem is.
The mass of person A, so the guy that's...
There's like 10 different ways to ask this question, just so you guys know. So let me tell you all the different ways. There's how fast can let's just say this is person A and this is person B. How fast can person A accelerate up the rope and not lift person B off the ground? That's a version of this problem. There's another version where I give you an acceleration of person A and ask for the acceleration of person B, and they don't have to be the same. There's the case that I've given you in this one, where I give you an acceleration of person A and ask for their mass while person B is still on the ground. That's when you were given. But there's a lot of variety here. So be aware that we can play around in the variety a little bit. Let's assume for the time being that person B is touching the ground and person A is accelerating up the rope. Okay? So, first things first, what am I going to draw? That's right. My favorite. A free body diagram. Name a force acting on person A. So I'm going to say MA times G for mass of person A times G. That's their weight. Anything else? What? Tension. Yeah, speak up. I'm going to make the tension greater than the weight. Why? Look, the tension acts on them. They pull down on the rope pulls up on them. And that's what causes them to accelerate. But the only way they will accelerate upwards is if the upward force is greater than the downward force. Okay? Everybody understand that? That's an important thing to understand. Is there any other force acting on person A? Then we are done with person A. Cue person B. Name a force acting on person B. Gravity. I think that it's not too much to ask to make person B's weight bigger than person A's. Doesn't that seem logical? Not even reasonable, just logical. Good. Now, are there any other forces acting on person B? Name one. Tension. I should draw that arrow the same size as the arrow drawn over here, because in our pulley system, the tensions are the same. Why? Because our pulley has no mass and no inertia. Now let me be very clear about this. That's not going to be the case all year. The tensions are the same right now because no difference in tension is required to turn the pulley. But the moment the pulley has inertia, it will take an unbalanced force to get it to turn, which means there will be differences in the tension then. But lucky for you, that's second semester. So you have a chance to drop by then. I'll be sad. Well, it depends on who you are. Just to be, if we're all being honest. But I'll be sad for most of you. Oh, because I don't think we can get along without all of you in this class. And now we have Stephen, and I'm pretty happy about that. See? It's going to be a good day today, Stephen. It probably hasn't been so far, but it's going to get better. I promise. What lunch do you have?
Second.
Oh, that sucks. All the good people are in first lunch.
Yes.
Yeah, lunch A. What the hell are you cheering for? I was going to say that if you had lunch A, you're welcome to come up here and eat in my room. But you have lunch B, so there'll be a whole bunch of fourth period people in there, and they will look at you funny. They're weirdos. And you can quote me on that. My fourth period is. All right, so we're done with this, right? No, we haven't even begun the problem. Let's go ahead and begin the problem. Net force. That's where we go next. Now, I want to point out, you should draw a coordinate system. And drawing a coordinate system is your opportunity to make a decision about what is positive and what is negative. In a problem like this, that is essential to getting the answer correct in a way that I can't fully emphasize enough. Now, to make this decision, what I would consider doing is a consistent direction for positive based on acceleration. Now, we only have one thing accelerating in this problem, but I would still go with a consistent direction for positive. So I base that on the pulley. And I'm going to say positive is in that direction. Meaning anything that's up on the left side of the pulley will be positive. And anything that's down on the right side of the pulley, I'll make that positive. Problems with tension require a consistent direction for positive. I would really encourage you to do so. So, moving on, I'm going to make this direction positive and this direction positive. Are we good? Now, you've noticed I am just going through the set of steps. I have not veered from the set of steps yet. I'm now about to employ Newton's law, and person A is accelerating. So person A will get Newton's second law. In fact, I should be a little bit more critical here. This is mass of person A. And person B, I'm going to employ Newton's first law because they are on the ground. And we are told that they stay at rest. Net force equals 0. Now, to keep my emphasis firmly in place, net force means to add up all the forces and set them equal to whatever's on the other side. This is a set of instructions. I need to follow those instructions. So I'm starting with person A. There are two forces that act upon them. Tension is upwards, therefore it's positive. Their weight is downwards, therefore it's negative. And I'll set that equal to MA. Still following my set of steps. Person B has three forces acting upon them. Their weight is downwards. I'm making that positive. Minus their normal force, minus the tension, because those are upwards. They are negative. Yes.
It says in the problem that they lose contact with the floor.
I'm not done yet. Set that equal to 0. Now, this is what your set of steps should get you. Maybe with or without the normal force. Now, the reason I left it in there is because they're not accelerating, and I want to prove a point. So if I may, if we look, there is something that brings these two problems together. The tension. The tension in the rope is the same for both. Now, if you look closely, and I would encourage you to do so, tension equals MA times G plus the acceleration. I've combined two steps in one there, right? I moved MG over to the other side, then I factored out the mass. Now, I'm doing this to prove a point, that the smallest the tension could be is their weight, unless they're accelerating downwards. But if they just hang there, then this acceleration would be 0, and the tension would be the weight. You follow me? You follow that description? So if they weigh 600 newtons, and they just hung on the rope, based on this relationship, if they're not accelerating, the tension in the rope would be 600 newtons. Is that okay? If they're accelerating upwards, the tension increases. Do you understand that? That as they start to accelerate upwards, they will be pulling harder on the rope, and therefore there will be more tension in the rope. The reason that's important is look over here. The normal and the tension are both equal to something that cannot change. Right? The weight of the guy that's on the other side isn't going to change. That's a constant. Now, they could go on a diet, but that's not going to be in the scope of this problem. So their weight's going to stay constant for this problem. Both of those have to add up to be the weight. Now, the tension is related to what the guy on the other side does. The ground simply responds to that. So the harder that guy pulls, the less the floor has to actually work to keep this guy in place. If he pulls up hard enough, the floor won't hold him at all. That's a threshold question. There are problems that have thresholds. A point where something happens, where there's a maximum, a minimum, or a 0. We look for thresholds. The threshold here is that there's this instant where the ground doesn't have to support their weight, but they're not accelerating yet. It's like they could just lift their toe off the ground. They don't go anywhere, but the ground wasn't doing anything anyways. That's the threshold. If this guy over here accelerates any faster, he's going to start lifting this guy off the ground. But at this instant, the ground isn't necessary to hold him in place. That idea that you would put a 0 in for the normal force is important. That requires you to think. It's a reasoning skill. Now, in this problem, I just told you that the normal force was 0. But that doesn't have to be the case. It's, to me, just as good that you be able to reason out what to do at a threshold. So everybody understand what I'm saying? You have to look for a threshold. I'm going to be pretty blatant on your test, but I want to be very clear that that doesn't have to be the future of this. I would like you to be able to reason this out. I could also see that as part of a discussion question. I mean, what would it mean for the person to not be touching the ground anymore? It would mean that the normal force would go to 0. I could see that as a discussion question. And I'm not hinting. I'm telling you, there's going to be a discussion question on your test. Be prepared for it. All right. Now I can finish the problem, by the way. The problem was to figure out this guy's mass. And I now have a method to do so because the mass of this guy hanging is related to this guy who's just stepped off the ground. Now, I've kind of written all over this one, so I'm going to go to a fresh place to continue this problem, okay? But I've done all the heavy lifting. So T equals mass of person A, G plus A, and T equals mass of person B times G. Right? So, bring these together. Mass of person B times G equals mass of person A times G plus A. Now, there's probably numbers here. I don't know what the numbers are.
80 for the mass of person B.
Oh, I'm not going to put them in. I think I've done enough, haven't I? Can you figure out how to go from here? Is there anybody who needs me to continue this? Okay. Yeah, let's do that one. That's all right. This one is, I would not do this to you on the test. Wait, let me finish, because you don't know what I mean. I would give you the mass of the book. Otherwise, you have to do this in terms of the mass. And that's not particularly obvious, because I give you the coefficient as a number. Should have given you the mass as a number. But let's talk about this problem anyways. There's absolutely nothing wrong with the problem itself, the basic premise of the problem. A force is applied to the book to hold it against the wall. We talked about this too, as I recall. We did it with an angle, which I think makes it harder, but doing it like this isn't all that bad. When I look at all the forces acting on the book, and I'm gonna go a little faster now, I see 4 forces acting on this book. There's your applied force on the book, your hand on it. There's the book experiencing a normal force from the wall. There's the weight of the book. And then there must be an upward force. What do you think causes the upward force in a book? It's gotta be friction, yeah. It's gotta be. It's a force that will prevent one surface from sliding past another, the book sliding against the wall. My expectation is the net force in this system has to be 0. We want the book to stay in place against the wall, which means I can split this up into the net force in the x and the net force in the y. Both of them equal to 0. I will choose a coordinate system like so. And in the x direction, I will have normal minus the applied force equals 0. And in the y direction, I will have friction minus weight equals 0. Now, normal equals the applied force. Friction equals the weight. I don't really know what the question is, but I do know that static friction is less than equal to mu s times the normal force. In order to preserve the direction of the inequality, I recommend substituting into the inequality when able. And we are able. So I'll put the applied force there for normal. And this all becomes the frictional force. And I will get mg has to be less than equal to mu s times the applied force. My understanding is we are looking for the applied force.
Yeah.
So I will divide both sides by mu and get the applied force must be greater than or equal to mg over mu s. Yes, mu is 0.7, g was 10. You could put that stuff in there, but this is largely the answer. I like expression answers, by the way. I like them for a number of reasons. First, you can't convert the units wrong. If it's an expression answer, there are no units. Second, you have extra ways to check your work with expressions that you don't have with numbers. For example, my answer was supposed to be a force, right? Well, you can check with your expression whether you get units of force. It's a way of validating whether you did your algebra right. Mass is supposed to be in kilograms. G will be in meters per second squared. Mu has no units. That is the unit of force. It is likely I did my algebra correct because the units appear to validate and back that up. So that's why I like expression problems. You probably don't like them right now. It doesn't really matter. You have to do them. So you will have at least one expression problem tomorrow and one mathematical problem tomorrow. Is that all, or would you like me to do anything else with that?
I just have like a general question.
I have a general answer, but I just want to show you something, okay? You can't actually cancel anything out. Just so we all know that we use that word because that's what effectively it looks like in mathematics, but we actually don't do that. And the reason is simple. There is no cancellation property. There's the multiplicative property of algebra, which is what we're actually using when we say we're canceling something out. But we're actually using what's called the identity property to turn something into a 1. And then because there's a 1 there, we're able to say 1 times anything is itself, the identity. So if I have ax plus cx equals c, there's actually no way for me to divide both sides by c and remove it from the equation. But people in this room have been trying. But writing it like this, I think, shows a little bit why. What you guys want to do is you want to cancel out 1 on each side, because there's 1 on each side. But that's not what we do when we do this process. The actual process would be factoring first. I'm going to change the rules a bit for something that can be done. Factoring first. Right? Then using the multiplicative property of algebra to divide both sides by the same thing. So I could divide this side by x and this side by x. Then regrouping using the associative property. Right? Then identifying that a number divided by itself is equal to the identity. And I know you think this is terribly long-winded, but this is what you actually did in algebra. And now a number times the identity is itself. So likely what your teacher did is said that you can cancel it out, because that's effectively what we're doing. But the reason why they actually make you do all this when you're in algebra and talk about what the different steps are is this actually makes you force yourself to assume that x is not 0. And so they want you thinking about that, because it is possible, especially in this class, when we divide by a variable, that variable may very well be 0 sometimes. And they want you to think about it when you do. So that's the first thing. And because we do a lot of expressions, it is very plausible you'll have times where a single variable will appear in a place that is inconvenient for what you want. And the example we've seen is something like t minus mg equals ma. And you want a. And maybe you're not allowed to have m in your answer. You can't cancel it out here. And the reason is because it can't be factored from both terms. That's the issue. So we could divide both sides by m, sure. And on this side, it would go away by all the properties we just talked about. But I could not do it here because I do not have an m in both terms to which to factor it out. But look, if we get disturbed by the bell, just so you know, this problem was completed during 5th period. So it will appears in its entirety. But I will get started with it because it's a good question. You are first asked to figure out what the frictional force is acting on the dime. So, free body diagram, weight, normal force, and, hope not a surprise, friction acting towards the center. Now, just don't be surprised by this, but remember, if this is the record and here's the dime, the only way it travels in a circular path is if there's an unbalanced force that is acting towards the center. Otherwise, it will speed off, and whatever the last straight line was that it was traveling, something has to cause it to turn. That something in this case looks to be friction. It's the only force that can prevent it from sliding. So it's got to be the frictional force that causes it to turn. Now that being said, we were given mu in the problem. I don't remember what it is, but we were given it. 0.4, I think. We were given the mass of the dime, 10 grams. It's 0.01 kilograms. And I know that friction is mu times the normal force. It's an inequality, but they asked what the maximum frictional force is. So that occurs when I set my inequality to an equality. Now, we've done enough of these for me to probably jump through the part where I do net force in the y direction equals 0. Can we all just kind of jump in and say normal equals weight on this one and be okay with it? Or do you want me to draw in a coordinate system and do the whole thing? All right, good. So There we go. That's the answer. You plug the numbers in, you'll get it. And I think when you plug all the numbers in, you get a force of 0.04 newtons. Now that part's pretty straightforward. It's what happens afterwards that gets this a little bit trickier. Because then they ask questions about, well, the record spins at 33 1/3 RPM. What is the speed of a point on the edge of the record here? And I expect you to know how to do this. I know I expect a lot, but I don't think this one's tough. But I think you think it's tough. How many of you would like me to show you how to do that? I had a feeling. So, by the way, no longer teaching, downshifting into reviewing. 33 1/3 rotations per minute. Well, let's hit that low-hanging fruit. We want meters per second. So let's get rid of the minutes and make seconds, shall we? I'm going to put minute on the top to cancel the minutes on the bottom. And I'm going to put seconds on the bottom because I want it as per second. Now I need to come up with a conversion fact. Do you know a conversion fact that can get me from minutes to seconds? I'm really not asking that. That's pretty rhetorical, right? So some of you will still reverse this and put the 60 with the minutes. You all are crazy. Now here's the hard part. And not the part that I think is hard, but the part I think you think is hard. Just a reminder. It's a record. They're round. I said as if you guys didn't know. The little thing in the middle. That was supposed to be a circle. That did not work out as a circle. And a dime right here. Now, every time this sucker makes a rotation, how far does it go? What would you call that word about how far it goes? So, it could be stated that every rotation is 2 pi r meters. Right? A circumference. Tell me you didn't know that. How dare you? I dare you to tell me. I pity the fool who doesn't know that. Rotations cancels. Minutes cancel, and I'll be left with something in meters per second. So let's handle this. It's 33.3 times 2 pi times 0.31. You better put your thing in meters. If you left that radius as 31 centimeters, you'd get centimeters per second. We don't want that. All divided by 60. You can do the rest, right? It's like, by the way, it's like 1.08 meters per second. I want to be, in the other classes, just so you guys know, I started everything by being very meticulous and slow, with the point being that I took about 12 to 15 minutes to explain the first question that was asked. I did that purposefully because I wanted students to get an idea that I believe the test questions, when explained slowly and thoroughly, will take about 12 to 14 minutes to explain, suggesting that for me, the pacing for the test would mean that a problem of this nature would take you 10 minutes or less to do. That's what I am looking at for pacing. So you should expect any one of those kinds of problems that you were given to be a 10-minute question, but I will guarantee that every one of them that's offered has a writing component as well as the problem. Some of the ones that you have don't have a writing component because they were given 2 or 3 years ago when I wasn't doing as much writing. Now that I understand the AP exam more thoroughly, I give more writing examples, more opportunity for you to write. Every one of these questions will have a D or an E, which is going to ask for you to write me a couple of sentences. Does everybody understand? Okay. So I am expecting these to be about 10 minutes each. So you should expect 2 of them. You should expect one of them to be numerical in nature and one of them to be more expression in nature. So I also have like 4 different versions of the test. And you guys have seen the kind of variance in the problems, but it is unlikely a person at your table will have the same test as you, because it's just too easy to see their pictures and diagrams, even when you're not trying, right? And I'm not going to put boxes on your heads or between the tables. So that's the deal. Ready? You want the second part of the problem when the person accelerates upwards and you're asked to find the mass of that person. All right. So in that problem, and I want to be thorough. So one of the things I've told you guys is when you're dealing with a problem like this, don't be thrown off. Go back to your set of steps because they will help you solve the problem. So there are two objects here, object A and object B. Only one of them is accelerating. That's object A. Object B does not accelerate. So we can start this problem off by saying object B has a net force equal to 0 and object A has a net force equal to ma. You can start the problem there. We are expressly told the acceleration of object A. Now, I get the fact that there's some confusion about what's happening to person A. Person A is grabbing the rope and pulling down. That's their force on the rope. The rope's force on them is up. Everybody hear that argument? Because that's a Newton's third law pair. They pull down on the rope, so that force is on the rope, but the rope pulls up on them. So when I look at the forces on person A, there will be an upwards tension. And that upwards tension must be greater than the weight of person A because they accelerate up the rope due to this force. Questions about this? Yep.
So you wouldn't include anything about like what that person's doing like to the rope, like their force to the rope, because the rope's not the
That force acts on the rope. So you would have to look at the forces acting on the rope. But we don't have to study the rope. The rope has no mass. So because of that, we don't care about the forces on the rope. We might need that if you were ever asked to discuss the forces on the pulley. Then we would. But that's still just tension. Them applying a force of tension to the rope puts a force of tension on them too. It's like your arm. If your arm grabs something, you're putting a force on that something. But there's also a force you can feel in your shoulder pulling on you. Do you know what I'm saying? So it's an equal and opposite force. The one that acts on you causes you to do something. The one that acts on the thing you're grabbing causes the thing that you're grabbing to do something. So they pull down on the rope. That does something to the rope. But the rope also pulls up on them. That does something to them. Does that make sense? I know it's hard. Don't get me wrong. And let's be really clear what them pulling on the rope does. So I want you to pay attention to this because this is kind of the meat and bones of it. They pull down on the rope. That is translated by the pulley so that it pulls up on the other guy. Right? That's how this force makes it to the other guy, is across the pulley through the rope into his hands. So don't for a moment think that the person's actions on the rope aren't going anywhere. They are. They're going to the other guy. And his actions on the rope complete the cycle. If he doesn't hold on to the rope, there will be no tension in the rope, and thus the other person won't climb it. So both of these are all required to make this happen. So let's keep going. Person B, and I'm going to do something here that might go against what you think should be happening based on what's told to you in the problem. But I have a teachable moment here, and I want to use it. Person B is experiencing tension, and that tension should be the same because it's the same rope. Now, it was asked earlier today whether the two tensions or the tension in a rope is always the same. The answer is no. The tension won't always be the same. The reason it's the same now is your pulley has no inertia and your rope has no mass. As long as those are the same, then the tension in the rope will always be the same and you won't have to worry about it. The moment the rope has mass or the moment the pulley has inertia, that will no longer be true. For the rope to accelerate, there'll have to be an imbalance of force because it has mass. For the pulley to accelerate, there'll have to be an imbalance of force because the pulley has inertia. But as long as that's not the case, the tension will stay the same in the rope everywhere. So you have to make sure you judge the problem. Now, first semester, the pulley's never going to have inertia. So you don't have to worry about it right now. I'm trying to get you guys to just do these problems without that level of difficulty in them. Second semester, though, gloves come off. We're going to add some inertia to the pulleys. So you have until second semester to get a schedule change. If you don't want to do that, just so you know. All right. There are other forces acting in the system. All right. The person B has weight. And I don't think it's too crazy to think that the person might weigh more than the tension in the rope. And if they do, the floor must also push up on them to keep them from sinking through the floor. Now, I'm just looking at the arrows right now. If person A pulls harder on the rope, then that's going to make the tension bigger. And that'll make this side's tension bigger too, which means I might not need as much normal force. Of course, if person A doesn't pull on the rope at all, then person B is likely to need all the normal force they can get, right? To balance their weight. I'm saying all of these things because the normal force reacts to the conditions at hand. So if you pull hard enough, you might be able to get the normal force to go to zero. Heck, you might be able to lift the guy off the ground if you pull hard enough. I want to leave it like this for a moment, though, because we're talking about something called threshold. This is a threshold problem. There is a point where a threshold is reached. And threshold problems are a little unique. They require you to do some thoughtful decision making. Now, right now, I'm not going to do any decision making. I've drawn these arrows because this is the way the arrows get drawn. I don't have to decide anything that I've done here except for maybe their size. But ultimately, even their size, I don't really have to worry about too much if all I'm doing is walking through my set of steps blindly. Does everybody understand? You would still draw these arrows the same way you did. They just might not be of the right size. I'll say this, though. You could continue blindly by saying person A has a net force equal to MAG. Not G, sorry. MAA. They're accelerating. And based on what I've chosen for the direction, right? I put this little arrow in here to indicate this is going to be the positive direction. With a pulley problem, you need to indicate direction. Something that is consistent for the entire problem. So I labeled the pulley the direction of positive because I believe from the pulley it kind of extends. This side has to be positive because that's the direction that goes positive with the pulley. And this side has to have downwards positive because, again, that's the direction of positive with the pulley. So I just label the pulley as what I'm going to call positive. And from there, I would say that for person A, T minus weight equals MA times acceleration. And for person B, I'll have their weight minus tension minus normal equals 0. Now look, the tension in the rope is comprised of two contributing factors. Solved A for the tension. There are two things that contribute to the tension in the rope. How heavy person A is, duh, they're hanging there, and how fast they accelerate up the rope. Now, they decide how much tension's in the rope. If they accelerate quickly, they add more tension to the rope. Now, the other side, let's look at that normal force for just a minute. This normal force depends on the tension and the weight of person B. But there's a minus sign in there. You see the minus sign, don't you? That means there's a possibility that the tension in the rope could be equal to the weight of the person. All right, that could happen. It could be that the normal force is 0. It is possible to pull hard enough on the rope to lift person B. That's a threshold. An understanding that there is a moment where the person loses contact with the ground, when the ground no longer supports them. They're not accelerating, but they just kind of are holding that rope and they lift their feet up and they're no longer touching the ground. They're just sitting there. It's at that instant that the normal force goes to 0. They're not being lifted upwards, though. They're just not falling to the ground. That's the threshold of this problem. That's the important threshold. That's the instant they're talking about. They said the person accelerates up the rope at 2 meters per second squared, and it's at that moment that the person on the ground can just lift their foot off the ground and not accelerate upwards. That's what the problem says. That's the threshold. So, tension equals the weight of person B. Now, this still isn't the solution to the problem. This is employing all the steps and understanding what that statement was about when it said that the person loses contact with the ground. We still have to solve the problem, which is we need to take what we've been given and figure out how to use it. We want the mass of person A. So we're probably going to have to do some substitution. And I have first the tension equals the mass of person B times G, and tension equals the mass of person A times G plus the mass of person A times A. I think we set these two things equal to each other and get the weight of person B equals the weight of person A plus their contribution based on their acceleration. I think I can stop here. You want the mass of person A. You know the mass of person B, you know G, and you know the acceleration. I think you guys can do the rest of this problem. You're just solving for MA. Or do I need to finish the problem?
I just kind of get confused at this step for some reason. I don't know why. It's probably really simple, but like I was like tripped up at can't.
The problem wants this, and I've worked with a couple of kids today, and I am seeing that you guys get tripped up with algebra. And I've seen several kids actually do algebra the absolute hardest way possible. Feel bad for you, but there's not a whole lot I can do to fix that except for practice. I'm going to collect terms. I want MA by itself. This side hasn't changed. You'll notice I'm doing this problem without putting any numbers in it, because I know you're going to have to do an expression problem. Now, again, I need MA by itself, so I'm going to divide both sides by G plus A. This will give me the mass of person A has to equal the mass of person B times G over G plus A. Now, we have all these pieces of information. What's the mass of person B? Is it like 80? So this is going to be 80 times 10 divided by 10 plus 2. What's that? Yeah, I think those were all given problems, given information. And that's the answer. I don't know what it is. 800 divided by 12. You can do that. I don't need the answer, by the way. So you guys can work the numbers. So it looks like that. And I don't remember if it has friction or not. All right, so we want the acceleration of the system or the tension in the rope. Probably both. So this is Again, I see nothing wrong with this problem. Again, I will start this problem the same way I start all problems, with a, that's right, Freebody diagram. Why not? You guys didn't all say it the way I wanted you to, so I'm going to go with, let's see, mg here, normal there, and tension there. Questions about that Freebody diagram? All right. The other one, there's no friction, so tension should be the same. mg, normal. Questions there? Yep.
So how do you know how big the tension is relative to like the normal force and the
I just made it less.
Okay.
How do I know? Because looking at this picture, it's this mass that makes the system move.
Yeah.
Should my tension be bigger than the weight of that mass? I don't think so either. That's why. So aside from that, I didn't have anything specific. I think these two arrows should be the same size. I really didn't make that happen here, but I would have liked that. And I think you should be doing it with a ruler on the test tomorrow. That's not a hint, and that's not a suggestion. You should have a ruler for tomorrow's test. Your arrow should be drawn very clearly with a ruler. So I'm going to continue my set of steps, which tells me to decide whether it's a first law problem or a second law problem. I think in both cases, it's a second law problem. These two masses are connected together and will accelerate at the same rate. I think they will accelerate that direction. So I'm kind of choosing that to be the direction for positive. The right side's easier, so I'm going to start with that one. That's the positive x direction. I'm not even going to look at the y direction. It's not accelerating in the y direction at all, and there's no friction, so I don't have to worry about the normal force. Are we all okay with that? I mean, if you want, I could do all the steps and say net force in the y equals 0, so normal minus weight equals 0, so normal equals weight. Great, that does nothing for this problem. But in the x direction, the block will accelerate because it's unbalanced. And how much it accelerates will depend upon the tension. That's the only force acting in the x direction. The other block is on an incline, and therefore studying it's going to be a little more difficult. I'm going to choose a coordinate system. Positive y, I'm making this the positive x direction. Again, I'm trying to make sure that I am consistent with what I call positive between both objects. It'll make my life easier. This is theta, and therefore I need to break up the weight into two components. And boy, I've done this so much. I'm really hoping this has begun to sink in some. This is mg cosine theta. And this one is mg sine theta. And I'd ask if there's any questions about this, but I really don't want to answer any if there are. Because we've done this a lot, haven't we? Kind of rubbed it in a lot. So, and I know I just shamed anybody into not asking questions, and I'm okay with that. Net force in the x direction equals 0. This I can tell who's paying attention and who's not. But is that true? No. Net force in the y direction equals 0. Net force in the x direction equals ma. There's two forces in the x direction. There's mg sine theta and tension. That equals ma. Now I could also talk about the net force in the y direction, but it is going to be useless for this problem. It equals 0, and normal minus mg cosine theta equals 0. Again, doesn't do anything. But I've done all of my steps now. All this was the set of steps you've already been given. I'm following it to the end. Now, eventually I have to solve the question. And the question is, what is the acceleration of the system? And here's, I think, something that's hard for you guys. We are allowed to have m and g and theta in our answer. Now I'm highlighting where m, g, and theta are, because those can be in our answers. It's like they gave us those numbers. Because these two equations then both have two numbers or two letters that can't be in our answer. Those are the unknowns. This is two equations with two unknowns. We need to find a way to get the acceleration and the tension. I'm going to do the acceleration first, but I'll point out I can't just divide this by m and say that that's my answer. If I do, it's got t in it, and it's not allowed to be in my answer. For the same reason why I can't take this and divide by m and say that that's my answer, because it'll also have t in it, and t is not allowed to be in my answer. I need to eliminate t. That's how this is done. So I'm going to substitute. Actually, I probably wouldn't. I'd probably do a different method, but for you guys, I'm going to substitute. So when I do, I get mg sine theta minus ma equals ma. I now have an expression with just one variable that I'm not allowed to have in my answer, a. And I was asked to find a in terms of the other variables that can be in my answer. So I'm going to isolate a. I'm going to get every term with a in it to the same side. I'm going to assume that you know that ma plus ma is 2ma. Not 0 and not ma. It's 2ma. And now I'm going to divide both sides by 2m. That goes away, and I'll get a equals g sine theta over 2. That's the answer. How do I know it's the answer? You don't. But I do know that acceleration is supposed to be in meters per second squared. I know that sine doesn't have a unit. The number 2 doesn't have a unit. And the unit of g is meters per second squared. So I know it's likely that my answer is right, because the units sync up the way they should. I at least didn't make any algebra mistakes. Now, that's not the only thing you're supposed to do. You're also supposed to find the tension. I would do that here. It's easiest. I just found the acceleration. So to find the tension, I'll take the mass and multiply by the acceleration. G sine theta over 2. That's the answer. It'd be nice to clean it up and have mg sine theta over 2. That'd be nice. But you don't have to. Again, sine doesn't have any units, but mg, well, that has units of newtons. So my answer's tension is supposed to be in newtons. That seems good. All right. Sure, is that pretty good? All right. Let's start the problem where it wants the maximum frictional force acting on the dime. Now, I'll just point out that I'm going to start this problem the same way I start all of these problems with what? Told you you'd be tired of this stuff by the time we got here. I suspect there are 3 forces acting on the dime. Weight, normal force, and friction, which I will draw towards the center of the record. Why towards the center of the record? Well, let me tell you why towards the center of the record. Here's the record. Kind of. I think it's the record. It wouldn't be white, though. Although I did have a white record once. I had a yellow one. I had a clear one. And I had one that had ET on it. Because at one time, I got the ET record, and it had ET on it. Because I was like 6 and thought ET was way cool. I know you guys are just laughing, but you thought when you were 6 some pretty whack stuff was cool, so it's okay. All right, so looking at the dime, the dime's traveling along with the record. The record would be spinning this way if we were looking down on a record, which means that the dime itself wants to travel in a straight line path like that. That's the direction it wants to travel. The only thing that keeps it from traveling in a straight path is if something causes it to turn. The force that would cause it to turn would have to be in that direction to cause it to turn. The only force from these 3 that can do that is friction. So friction must point towards the center, and it must be the reason the dime turns on the record. We can't come up with a new way of coming up with forces. But when we try to decide which force is causing it to turn, that's kind of how you do it. By evaluating what forces are acting in the system and decide which one could possibly point towards the center. Now that we've done that, the actual problem isn't all that tough, especially because of what they gave us. Net force in the x direction equals ma. It's unbalanced. Net force in the y direction is 0. Those are balanced. So normal minus mg equals 0. On the other hand, friction equals ma. I don't know what a is. I don't know how fast the system's going. I don't know what the acceleration is. So I can't find friction here. But they probably gave me the coefficient of friction for a reason. So maybe I can find the frictional force that way. And since they asked for the max frictional force, they're kind of directing me to the equation for friction, specifically the equation for static friction, which is an inequality. Look, I can get the normal force. The normal force equals mg. So the frictional force must be less than or equal to mu mg, which based on what they gave me was 0.4 for mu, 0.01 for mass, 10 grams is 0.01 kilograms, and 10 for g. That means the frictional force must be less than or equal to 0.04 newtons. And I'll tell you what, it asked for the max, so the max frictional force is 0.04. That's part A. Now, part B kind of cracks me up because you guys, I think you should be able to do it. It says that the record is spinning at 33 1/3 rotations per minute. They don't even ask you about 45 rotations per minute, but if you can do this for one, you can do it for both. They want to know how fast the dime is going. Look, you want to go? Go, but I'm going to explain this, so leave quietly because I'm recording. If we look back here, that equals ma. To figure this one out, and again, I would feel perfectly acceptable having this on the test tomorrow without explaining it. 33 rotations per minute. I know I left off the third. It's okay, right? First, let's handle the easy part of this problem. If I want to get rid of minutes and be left in seconds, I can do that. Close the door, please. For every 1 minute, there are 60 seconds. But the part that you might find challenging, how far does the dime go in one rotation? That's right, 2 pi r meters for every one rotation. That's what you would do. Now, I think you guys can put 45 in here and repeat. The last question's a hard one, though. Oh, it's perfectly acceptable for the test to me. Here's what you have to do. You just found what the velocity is. For this one, it comes out to be like 1.08 meters per second. And you're asked where on the record you could place the dime and it not fly off the record. Well, remember, 0.04 is the maximum frictional force. So that equals MA. But for a rotating object, that's MAC, which is 0.04 equals M times V squared over R. Right? Find R. You know what everything else is. You got me? You found the velocity. So you'll have 0.04 equals M times V squared over R. You can use that to find R. Now there's a little problem with this, which is why I won't have it exactly like this on the test. But this kind of figuring is something that I feel is okay on the exam.